So let's talk about load balancers. Load balancers are one of the most important infrastructure components out there. We have literally started taking it for granted because whenever we think of, hey, I want to scale this API server, you just say, hey, I'll just put it behind load balancer. They are so essential in building horizontally scalable system. Let's spend some time understanding what they are, what the key and what they hold as their key features, right? Okay. First point first. Load balancer is effectively the only point of contact. So what happens is whenever a user wants to reach out to one of the backend API servers, they have to go through load balancers. So now what load balancers give you, the first feature that they give you is they give you a single point of contact. Through this single point of contact, any client will reach out to this. Like for example, let's take a step back. What if there wasn't any load balancer? Then what would have happened? Let's say you have bunch of API servers lying around, right? Now, it would be the responsibility of your user to know the IP address of the server to talk to. How would they get it? Right? Now what load balancers does beautifully is load balancers typically have either a static IP address or a static DNS name. With this, what happens is your clients only need to know that one thing to talk to it. They don't have to know what all API servers are there, what are their IP addresses and whatnot. So load balancers abstract out these details for you by being the first and the only point of contact for you to talk to any of the backend servers, right? And this is the beauty of load balancers because it is abstracting out the distributedness of your system, right? Okay. So given that it is abstracting out the servers that are lying around, the servers that are behind them, now what happens is you get horizontal scalability. So which means that you don't know, or your users don't need to know, that behind the load balancer there are 1 server, 2 server, 5 server, 50 server, 100 servers, 1000 server. For users, it just, oh, I have this load balancer name, I'll make request to that. I don't care how it goes past that, right? That's the beauty of it. Okay. So now when you have a load balancer, how does a request flow look like? So your client would already need to know the IP address or the domain name of your load balancer, right? Once they have this IP address or domain name of the load balancer, now what happens? Client makes a request to this IP address or domain name. The request comes to the load balancer. Let's say the domain name of the load balancer is auth.example.com, right? So request would come to this load balancer. Now it's responsibility of the load balancer to forward the request to one of the backend servers that it has. So out of n backend servers, in this case 3, it would pick one depending on a load balancing algorithm. We'll touch upon that in 2 minutes. It would pick one server using a specific load balancing algorithm. It picks that server, it makes the exact same request to that server. That server responds, the response comes to load balancer, and load balancer responds back to the client making the request. This way, you have only one point of contact to talk to. User talks to load balancer talks to one of the backend servers, gets the response, sends it back to the user. Okay, one point. The user that I'm talking about might not only be end user like us, might not only be humans. It can be some other service. Let's say your authentication service wants to talk to your profile service. So auth service, the API servers of auth service would make call to load balancer of profile service and get things done. They don't need to know IP addresses of the backend servers of profile service running it. Similarly, when any two service typically communicates, it's one API server and one load balancer communicating. So auth service want to talk to profile service, it goes via profile services load balancer, right? This is what abstracts out the distributedness of the system. Keep this in mind that whenever I draw this user icon or logo or this representative doodle, it does not just mean an end user like end human user like us. It could be anyone who wants to talk to this API server. Load balancer beautifully abstracts those things out for us, right? Okay. Now, the name suggests it's a load balancer. That's the job of it, to balance the load. Now, how it balances the load? It balances the load using some algorithms, because now the whole game is about picking one server to forward the request to. How do you pick one? Right? So which is what is defined by load balancing algorithms. First load balancing algorithm that we would look at is the one of the most basic one out there, called round robin, and by default almost all load balancers start with this. So in round robin, what happens is whenever a request comes to load balancer server picks the first server to forward a request to. Second request comes in, it goes to second server. Third request comes in, goes to third server. Fourth request comes in, goes to first server again. So it goes in round robin fashion. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, so on and so forth. As soon as a new server joins the group, it starts getting the request in a round robin fashion. This way, you see a near uniform distribution of requests happening across the infrastructure, right? This is where round robin algorithm shines. Okay. The second is weighted round robin load distribution or load balancing algorithm. In weighted round robin, what happens is, let's say I have 3 servers, first server, second server, third server, and the way I have defined or the way I have provisioned this server, I have, let's say, first server that has 4 GB of RAM, second server has 8 GB of RAM, third server has 4 GB of RAM. So my infrastructure is not uniform, which means that now if I do round robin, I would get 1, 2, 3, 4, 5, 6, 7, 8, 9. The problem is, because my second server is 2x larger, it can typically handle 2x more requests. Correct? So now it would be unfair, or rather I would be underutilizing my hardware if I only send it n requests. I should typically send 2n requests to second load balancer. So what I need is I should be round robining it in the ratio 1:2:1, which is what weighted round robin is all about. So in weighted round robin, you define the weights for each of your server, especially when your infrastructure is non-uniform, such that if, let's say, your ratio is 1:2:1, your request would go like this: 1, 2, 3, 4, 5, 6, 7, 8, right? 1:2:1 in a round robin fashion, right? And where would you use it? You would use it when your infrastructure is non-uniform. Your backend servers, they don't have the exact same configuration. Some are smaller, some are larger. So you define a weighted round robin scheme there. Right? The next algorithm is least connections based. Now in least connection based, what you do is your load balancer, because every time the request comes in to the load balancer creates a request to the backend server. Once it gets the response, the connection is typically terminated. That's how HTTP REST works, right? And when that happens, right? And when that happens, it means that the number of connections that the load balancer has to one of the backend server determines how busy the backend server is, right? So with least connection based approach, what we are doing is we are picking up one server, like the server that is having least connections from load balancer, which would mean that this server is more likely to be quote unquote free from serving the existing request, right? So that is where what you do is you are picking up server that is relatively free as compared to other servers. This way you are minimizing the response time or minimizing the load on a particular server. You are always pushing request to a server that is having least connections from the load balancer, right? This is least connections based approach. Now, where would you use it? Least connection based approach is a very good use case when you have request that, or when a service that you have written does not or have a very high variance in response time, which means, for example, if the service that I have written has high variance time, let's say some HTTP request might take 1 second, some request might take 5 minutes, very high variance, right? So what you do, because you are having very high variance, you would typically want to send request to a server that is relatively freer. Let's say one server gets 2 big requests to handle, and if you bombard it with other requests, then the new request that you send, it would take enough time to complete while other servers are free enough, right? So that would be unfair. So least connection based approach is very useful when you are having your backend servers, your service that you are written, which is serving through the servers, the service has very high variance, which means there are a lot of requests that is happening within 1 second. There are something which are happening more than 10 seconds, 15 seconds, even minutes per se. Right? So this way you are always prioritizing picking a server that is relatively freer. Right? And the degree of freeness is proportional to the number of connections that load balancer has with the backend server. So it always picks the one that is having the least connections from the load balancer. Right? And this is where you'll use least connection based approach. And the final algorithm that I'd like to talk about is hash based routing. It's very simple. What you do is when you get request, when your load balancer gets request, depending on some parameter, be it IP of the user or maybe user ID or maybe URL of it, right? Depending on whatever you are receiving, pick a particular parameter. It would take the hash of that and do a mod of number of servers you have in the backend. It would get one of the servers and load balancer would forward the request to that. Right? So because it is hash based, hash functions are deterministic. So for the same input, hash function would give the same output, which means you can build sticky sessions with this. Now what is stickiness? That when I want all the requests of a particular user to go to a specific backend server, I have to use hash based routing. So whenever a request comes in for a particular user, I would hash it. I would know which server I want to go to because it's what hash algorithm would spit out, and it would always go to that specific server no matter what. So it is, and plus hash functions are near random. So you would see almost uniform distribution across the servers, but it would be sticky with respect to the parameter that you are picking in. Let's say your parameter is user ID. So all the requests for a particular user will always go to a particular backend server. This is what your load balancer would ensure because that's how it is doing. User ID passed with the hash function, you get some number, you do a mod with 3, you get either 0, 1, 2. For the same user ID, you would get the same number. So your load balancer would always send request to that same server. Right? This is what you get with hash based routing. So when you need stickiness, you go for hash based routing. Right? These are some algorithms that are very common, that are very configurable. Almost all load balancer have these as part of their configuration. Right? So play around with any load balancer and understand and tune it, tweak it, and see how your load balancer reacts to that. Right? Now, key advantages of load balancer. Why are people using load balancers? First and most important one is scalability. Because now, given that a load balancer is abstracting out the distributedness of your API servers, what you can do is you can seamlessly add more servers behind a load balancer. For example, if let's say I wanted to handle 200 requests per minute and I know that one API server can handle 100 requests per minute, I just add one more. I would start handling 200 requests per minute. But let's say I know there is a sale upcoming and now I need to handle 300 requests per minute. I'll just add one more API server behind the scenes, right? While scaling the database, of course, but seamlessly scaling or seamlessly being able to horizontally scale the backend servers is a big thing, because now you can scale up your servers whenever you need it without having to make any complicated changes whatsoever. That's where load balancer abstracts out those complexities for you, because it is being the only point of contact for your end user. When you're making the call to the backend, that's the only point of contact. So you don't have to worry about anything. So you can seamlessly scale up and scale down your infrastructure. Second is availability. Now, because load balancer is abstracting out the distributedness of your system, if one of the server goes down, load balancer would just stop sending requests to that server. It would continue to send requests to other servers that are available. Which means that even if one of the API server crashes, there is no problem. There is no major outage. And load balancer would seamlessly forward the request to the servers that are healthy. And that's the best part of it. Right? And these two advantages are so massive. That's where load balancers have typically become quote unquote household names. You put it in every single infrastructure that you have. Almost every single set of API servers are put behind a load balancer, and we have almost started taking it for granted. Right? So yeah, that's all what I wanted to cover for load balancer. As part of exercise, what I would like you all to do is go through AWS load balancers documentation. See the kind of features they provide, see the kind of configurations they have. Watch YouTube videos where someone has given a walkthrough of how to configure AWS load balancer. If you have AWS account, brilliant. In case you don't, just absorb the kind of things AWS load balancer provides. You would get detailed understanding of what load balancers are and those micro configurations that would make you understand this really well. Right? And yeah, that's all what I wanted to cover as part of load balancers. And I hope you found it interesting. Hope you found it amusing. That's it for this one. I'll see you in the next one. Thanks a ton.